Hello everyone, this is Mr. Huebner. In this video I want to talk about molecular geometry in respect to VSEPR theory. So essentially molecular geometry is the shape that a molecule will basically take based off of the electron repulsion of its lone pairs and the electron groups it has in the bonding pairs and the other things it's connected to. So what does VSEPR stand for? Let's see, let's get over here. It stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. And essentially what it is, I got this little model diagram. You can see it's essentially, it is a 180 bond angle. It's a line. This is a central atom. Right here are two outer atoms. And this line, remember, represents one pair of electrons that are being bonded. One electron from the center, one electron from the terminal or outer atom. And they are both being shared so that they can satisfy their octet and have 8 outer electrons. But what happens if you have a lone pair, a pair of electrons that are on the central atom that are not involved in bonding? Well, look at what it did to the bond angle. We originally were at a line 180, but now it's at an angle of 120. If you add another lone pair, you can see it further bends it because of the repulsion of this pair of electrons against this pair of electrons and these electron groups. It's bending it further. So let's take that one away. It was 120 and now it's 109.5. And you could actually add a third one. This would be an expanded octet where you have more than 8, and the repulsion of an extra lone pair combats the other lone pairs to then make it linear again. And in this model you can actually even put a fourth one lone pair on there. Now, can you have more than one? Yeah. Can you have a double bond? There are so many different possibilities. We in this course are just going to focus on 5 basic structures or shapes that a molecule can turn into. Are there more than that? Yes. Ooh, meteor shower on Earth Day. All right. There are definitely more shapes, but you're going to have to take AP or IB Chem to learn about those, because we're on a tight schedule here. Alright, so let's go and talk about some examples. We have valence shell electron pair repulsion model. Good chance that might pop up on a test. This feels like a good multiple choice question. We have different shapes. We got linear shape, we got trigonal planar, we have tetrahedral, we have pyramidal, and bent. I'm going to call this trigonal pyramidal, because that's what it's called, trigonal pyramidal. Alright, so let's start with linear. And description is going to be 2 outer atoms. I call them terminal atoms, or that's the technical word. I just call them outer, whatever works for you. So we'll call those terminal or outer atoms. And let's see, so it either has just 2 outer atoms and then also 0 lone pairs. Alright, and the bond angle this is going to form, linear line, is 180 degrees. I'd have to do a whole thing to put a degree symbol in, but it's 180 degrees. There we go. Alright, so let us do an example. So where we would put this, it's too hard to do it digitally. I can't write with my finger. I gotta have a pencil or pen. Coming up with an example of linear. Alright, I got one. We could do HCl, and of course you guys wouldn't know it's linear until you draw the Lewis dot structure. I just know from experience. There's a couple linear. We got HCl. Let's start with that one. So 2 ways to do this. You could do it the way that we went over, which is a very simple way. I call it the middle school way because it works for simple ones, but not for all situations. We'll do it that way first. So we got hydrogen, we got chlorine, and we have to go to the periodic table to refresh. How many valence electrons does hydrogen and chlorine have? So hydrogen's in the first column. Hydrogen is going to have 1 valence electron. Put a little dot there. And then we have chlorine is over here. And that's 1, 2, 3, 4, 5, 6, 7. So it has 7 valence electrons. Alright. 1, 2, 3, 4, 5, 6, 7. We have a little electron here and a little electron there. They want to pair up. So they don't want to be alone. So we draw a little line connecting them. And there's our HCl. Alright, so anytime we have just 2 atoms, there's really only one shape that can be formed. And that shape is a line. So right off the bat, we have linear for that one. Alright, so why don't we try the next one, CO2. Alright, so CO2, we got to figure out what's the center atom. Now, basically, in a nutshell, it's the one in least supply, which would be carbon because there's 1, and oxygen there's 2. So I'd put carbon in the center. That works most of the time. Some situation, you might have the same number of both elements. In that case, if carbon is one of them, carbon's always the center because carbon and silicon have the most bonding sites. That's what it boils down to. Whichever has the most bonding sites is the center atom. So why don't we just do an example? We got hydrogen as 1 valence electron, and then let's do beryllium as 1, 2. Moving on to boron has 3, 1, 2, 3. That's a lot of bonding sites. And then carbon has 1, 2, 3, 4. That's a lot. And then nitrogen has 1, 2, 3, 4, 5. Now we're back to just 1, 2, 3 bonding sites, not as many as carbon. And oxygen has 1, 2, 3, 4, 5, 6. Just 2 bonding sites. And then the halogens like fluorine, chlorine has 1, 2, 3, 4, 5, 6, 7. Just 1 bonding site. And the noble gases, they have 0 bonding sites, which is why they're not very reactive. Can they form compounds? Yes, they do when they break the octet rule, which we're not going to get into in this lesson. 1, 2, 3, 4, 5, 6, 7, 8 outer electrons, and there's no bonding site. So if we are looking at C and O, oxygen has 2 bonding sites and carbon has 4. Carbon's definitely going to be in the center. So I'm going to put carbon in the center and oxygen to the side, oxygen to the side. Alright, so we know that carbon has 4 and oxygen has 6. 1, 2, 3, 4, 5, 6. And what we need to, oh my gosh, I'm not showing it on the video here. So right here, we got carbon in the center and oxygen on either side. Carbon has 4, oxygen has 6, oxygen has 6. Oh, let's zoom up on that. 2 dots right there. So what we need to do is connect the single dots. There we go. There we go. There we go. And there we go. And here we go. It's a double bond. A double bond. And now we're trying to figure out the shape. The shape, this has 1, 2 outer atoms. And on the center atom, it has 0 lone pairs. So the key is looking just on the center atom. We're not looking at the outer atoms at all. So when we're determining how many lone pairs it has for the purposes of shape, we have to look at just the center atom. And it has 0 lone pairs. And what we said earlier was 2 outer atoms, 0 lone pairs. therefore it's linear. So those are two examples of linear. Alright, just for fun, I want to show you the way that works in all situations. No matter if it's a tough one or if it's an expanded octet, this situation, this method works in all cases. So first thing you need to do is, let's say we're doing CO2, you pick the center atom, and then you got outer atoms, and they have to be connected with at least one bond. So there we go, we got 1, 2 already. 1, 2, and then what you have to do is you count how many valence electrons these elements have. So we've got carbon has 1, 2, 3, 4, and oxygen has 1, 2, 3, 4, 5, 6. So we got 6 plus 4 plus 6. And that equals 12, 13, 14, was it 16? 12. Yeah, 16. All right. So, and again, I got to show this, sorry about that. So we got 6 plus 4 plus 6. Oxygen, carbon, oxygen. It equals 16. And we have 1, 2, 3, 4 electrons worked out already. We got to add them to the outer atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to stop because I got 1, 2, 3, 4, 5, 6, 7, 8. It's satisfied. So I got my total of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. And I got 2, 4, 6, 8. So this is happy. But carbon only has 1, 2, 3, 4. It is short 4 electrons. So what I can do is I can take 2 from this oxygen and share it. And so now I got 1, 2, 3, 4, 5, 6. This oxygen still has 1, 2, 3, 4, 5, 6, 7, 8. Because I didn't lose any, I'm just sharing them now. And typically the rule of thumb is symmetry is lower energy. So instead of having a third bond here, what I'm going to do is I'm going to take 2 from the other side to make it symmetrical. And I got 1, 2, 3, 4, 5, 6, 7, 8 now on carbon, and 1, 2, 3, 4, 5, 6, 7, 8 on oxygen. This way might be a little bit trickier in this regard, but when we get to really difficult ones, and then even into the expanded octet, this method works every single time. Whereas the middle school way only works for the simpler, easier ones. But who wants to just do easy? Alright, I'm feeling like we're ready for another shape. So why don't we go on to it? Looks like the next one is trigonal planar, or trigonal planar, however you want to pronounce it. Let's see, I would go trigonal planar. And so in this one we have 3 outer atoms. Might have to pause the video. Sounds like there might be some meltdowns in the other room. Let's see if my wife can handle that. Alright, 3 outer atoms. And it has, again, 0 lone pairs. So, very similar to linear, the difference is we have an extra outer atom. So we're going to have 4 total atoms instead of 3. And this is going to be 120 degrees. Alright, let's do an example. Why don't we do aluminum trichloride, or aluminum chloride, AlCl3. So right off the bat I got 3 chlorines, 1 aluminum. Which one's going to be in the center? The one in least supply, which is aluminum. I could also look at it this way. Aluminum has 3 outer atoms, whereas chlorine has 1, 2, 3, 4, 5, 6, 7. We got 1 bonding site for chlorine, and it looks like 3 bonding sites for aluminum. So aluminum having the most bonding sites is going to be in the center. Alright, and then we have chlorine. I'm going to do it the high school way, the way that allows you to do it every single problem. We got chlorine, we got chlorine, we got chlorine. And chlorine has 7 valence electrons, aluminum has 3. So 1, 2, 3, so 7 times 3 plus the 3 from aluminum. So 7 plus 7 is 14, plus 7 is 21, plus 3 is 24. All right, and I got to have at least one bond connected to each of them, because otherwise they're not going to be connected. And that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'm out of electrons, and I stopped putting dots when I had 8 on each. 2, 4, 6, 8, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Tricky thing is, in this situation, aluminum and boron are in exceptions where they're okay with just having 6 outer electrons. And if we did it the middle school way, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. We connect single dots, connect single dots, connect single dots, and call it a day. Once we get into more advanced chemistry, we take APRI B, we can explore why these act the way they do, breaking their octet. But for now, they do, and just have to accept it. All right, so looking at it, we got 1, 2, 3 outer atoms, and on the center atom, there are 0 lone pairs, 0 dots that aren't involved in bonding. And that fits our criteria of 3 outer atoms and 0 lone pairs. Alright, let's move on to another shape, tetrahedral. So with tetrahedral, we not have only 2, not only 3, we have 4 outer atoms. 4 outer atoms. And again, 0 lone pairs. And the bond angle is 109.5. Alright, so doing an example of tetrahedral, very common one would be methane, CH4. It's like the classic tetrahedral example. And this one's a simple one. You could do it the middle school way. We got carbon, we said earlier, has 4 outer electrons, and that's why I'm putting it in the center, because hydrogen has carbon has 4 bonding sites, hydrogen only has 1. So the one that has the most bonding sites is in the center. We got H, we have H, we have H, and we have H. Connect the single dots, connect the single dots, connect the single dots. So we got 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy, it has 8. But what about hydrogen? Hydrogen only has 1, 2. Well, that's kind of goofy, but we learned about electron configuration. 1s2, 2s2, 2p6. What is that? I believe that's neon. Let's double check. Yep, that's neon. And so what does that mean? That means our outer energy is 2 for this case, for neon, and it has 6, 7, 8. The whole goal is to have 8 outer electrons because the p and the s orbital together have a capacity of 8 electrons. But what about little 1s2 here? The first energy level only has an s, doesn't have a p orbital. So therefore, the first energy level can only hold a max of 2 electrons. And so that leaves us with hydrogen and helium being the 2 smallest elements, the ones that have their electrons in the ground state in the first energy level. They only want 2, just 2. So hydrogen's an exception, it's going to want 2. A lot of things to remember. You got all these rules and then exceptions to the rules, which can be a little frustrating. All right, but why don't we do it the high school way, where we've got, all right, I got to have at least 1 bond to each outer atom. I know carbon's my center atom, and I've got carbon has 4 outer atoms, hydrogen has 1, but there's carbon has 4 outer atoms, hydrogen has 1, but there are 1, 2, 3, 4 of them. 4 times 1 is 4, plus 4 is 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm done. That's another way of solving it. But how do we determine the shape? Well, we look at how many outer atoms are there. There's 1, 2, 3, 4. How many lone pairs are in the center? 0. And remember, a lone pair is a pair of electrons that are not involved in bonding. So 4 outer atoms, 0 lone pairs, that has to be none other than tetrahedral. right, moving on to the next one, trigonal pyramidal. All right, trigonal pyramidal, this one, just like trigonal planar, has 3 outer atoms. All right, well, what's different about it? Trigonal planar had 0 lone pairs on the center atom, but trigonal pyramidal, this one has 1 lone pair on center atom. That makes the bond angle less than 109.5. Let me find the less than sign. Okay, I'm going to pause this until I find the... Alright, I found the less than sign on the keyboard here. Here we go. Less than 109.5. 3 outer atoms. Now, let's take a step back here. Why don't we go to this model right here, and we get rid of these. I showed you in the beginning we have linear, 1, 2 outer atoms, 0 lone pairs on the center. Typically, it's caused by there being a double bond present in some way, making it linear, which would make sense. So now the center atom has 2, 4, 6, 8. It's kind of like how CO2 looks. So now, why don't we do something that has 3 outer atoms. All right, 1, 2, 3 outer atoms, 0 lone pairs, probably because you have a double bond on there somewhere, kind of like this. So you got 2, 4, 6, 8 now. That's trigonal planar, it's a bond angle 120. But what happens when you add a 4th one? Well, now it bends it to that 109.5 angle tetrahedral, and there are 0 lone pairs on the center. But here we are again, trigonal planar. How do we make that into trigonal pyramidal? We add a lone pair and see how that lone pair, according to VSEPR theory, valence shell electron pair repulsion model, showing that pair of electrons that are not involved in bonding, a lone pair, are pushing this flat pinwheel down to make a pyramid shape. And so we call this trigonal pyramidal because it has 3 outer atoms and 1 lone pair on the center. All right. So why don't we go to doing an example, do a common example. NH3, nitrogen, we said, has 5 valence electrons and H has 1. Since nitrogen has 1, 2, 3 bonding sites and hydrogen just has 1, this is going to be nitrogen, the center atom. Why don't we do it the high school way? We got 5 plus 1 plus 1 plus 1. 3 hydrogens. 5, 6, 7, 8. So a total of 8 valence electrons. And you got to have at least 1 bond connecting the center atom to each outer atom. That's 1, 2, 3, 4, 5, 6. We are too short. We need to put 2 more somewhere. So what happens is we add the extras to the outer atoms, but hydrogen is the exception. It just wants 2. So that one's fine, that one's fine, that one's fine. So if everything's filled up on the outer atoms, then you got to put any extra electron you have on the center atom. And this is true even if it's an expanded octet, where it breaks the octet rule having more than 8 electrons on the center atom. So I put my extra ones as a lone pair on my center atom, and I have 1, 2, 3 outer atoms and a lone pair, 1 lone pair. And that's an example of trigonal pyramidal. All right, we've got one more shape. It is bent. So this is very similar to linear, and linear had 2 outer atoms, but it had 0 lone pairs on the center. Bent has 2 outer atoms, but it has 1 or 2 lone pairs. So depending on how many lone pairs are on the center atom for this bent shape is going to determine whether it's this bond angle versus that bond angle. So we're going to be focusing on 2 lone pairs. You don't have to worry about 1 lone pair. One lone pair, if you're curious, is less than 120. 2 lone pairs is going to be less than 109.5. 109.5. And let's show you in this diagram right here. So we got linear is 180. Let's plop a lone pair on there. That just bends it to 120. Right there, a little bent. But what happens if we add a second lone pair? It bends it even further. So 109.5 is much more acute of an angle than an angle of 120. So it just further bends it. And this is a more simpler conformation, a more common one, and that's why we're focusing on the one that has two lone pairs instead of one. So it's less than 109.5 is the common bond angle of bent with two lone pairs. So why don't we do an example? Common example, H2O. So oxygen, we said, has 6 valence electrons, 2 bonding sites. And hydrogen has 1 bonding site, 1 valence electron. Alright, so we got 6 for oxygen and 1 and 1 for the 2 hydrogens. 6 plus 1 equals 8. Alright, so we got oxygen's the center atom because there's 2 bonding sites. Hydrogen just has 1. And here we go. We've got 1, 2, 3, 4. Hydrogen only wants 2, so it's set. So we got to put the others 5, 6, 7, 8. Now if you put it like that, that's basically the correct Lewis dot structure. But if we're looking at VSEPR theory, take a look at this picture. We're seeing these on top, not one on the bottom. So technically, the true picture is going to be oxygen and the 2 hydrogens kind of branching off. And now you can see that looks very much bent, and this does not. And we can see it has 2 outer atoms and 2 lone pairs. It's the definition of bent, less than 109.5 bond angle. Technically, if we're looking at NH3, I forgot to mention this, this doesn't really look like a pyramid shape, but if I could redraw it, and I'm going to encourage you guys to do this, although I'm not going to be too picky if you don't, but just try to make it look like a pyramid shape, because that's really what we're trying to represent. A trigonal pyramidal shape for that NH3 and a bent shape for that H2O. And technically this aluminum with the 3 chlorines, I want to branch them out so that they're equally distanced from each other. Kind of like that would be a more accurate drawing. And tetrahedral, I mean, if you build it like that, that's fine. Technically, you need to draw it something like this. Would be a little bit more accurate because it looks a lot like the trigonal pyramidal. The difference is instead of a lone pair, you got another outer or terminal atom. Alright, so I think that's everything on VSEPR theory, molecular shapes. If you got any questions, shoot me an email, let me know. That was today's video lessons on molecular shapes according to VSEPR theory, which is valence shell electron repulsion model. Alright, have a good one.